Welcome everyone and good afternoon. My name is UK Joe, a senior software engineer from SAIDA lab, Samsung AI research team. SAIDA stands for Samsung SDS, Artificial Intelligence and Data Analysis. I'll be referring to SAIDA as SAIDA from here on. I'm here to present our reinforcement learning platform, SAIDA RL, originally developed for making and testing StarCraft AI. For those who are not familiar with what StarCraft is, it's a very successful online strategy, a game created by Blizzard Entertainment. Let me first introduce myself briefly. As I already mentioned, my name is UK Joe, and I joined Samsung SDS in 2007 as an application software developer and transferred to AI research team last year to work on reinforcement learning. And I'm also pursuing a master's degree in industrial engineering, studying game AI at Korea University in Seoul. There are 4 things I would like to cover in this presentation. I will begin with an introduction of our SAIDA RL platform, and I will then talk about how game AI is created, followed by a demonstration of SAIDA RL agents using StarCraft. Lastly, I will talk about our research and development activities. I don't plan to give a detailed tutorial on reinforcement learning, although I will show you how DeepQ network works with code snippets and examples. I'll be answering any of the questions you may have at the end of the presentation. The objectives of this presentation are twofold. First, I want to help you understand how reinforcement learning is applied to game AI with an example case of StarCraft. I will show you how it is to develop AI agent using our SAIDA RL platform, which is much easier to do than having them created from the ground up. I will talk about things that should be taken consideration when developing AI agent. Second, I would like to show you what our advantages and approaches are in solving problems associated with reinforcement learning. It would be great if this presentation can help to pique your interest in the area, hopefully interest you enough to have you use it to your research in the end. In this chapter, I would like to give you a brief introduction of StarCraft and reinforcement learning and what it means apply reinforcement learning into StarCraft. So reinforcement learning first received its spotlight when an algorithm DeepQ network beat human in Atari games. Soon after, DeepMind surprised the world by defeating a Korean Go player named Lee Se-do in the game of Go, an Asian board game, and again in January 2019, when it beats human in much more complicated game of StarCraft. Many attempts are being made to expand reinforcement learning beyond gaming world and apply to the other area in the world. But there is lack of environment for agent training and validation. Game is another world, said David Hasamis, the CEO of Google DeepMind. In the gaming world, you can create and use data as you wish and train agents quickly without having to worry about failure or recovery. You can also create and run multiple scenarios with different levels of difficulty and formulate metrics that are simple and straightforward for evaluation. I also like to point out that we are able to secure 110,000 replay data from pro gamers, which we plan to use in the near future. So StarCraft is still played mostly by professional gamers, since 1998 and requires a player to spend a great deal of time thinking out strategies to win a game. There is a constant flow of new winning strategies that are being studied and made available to the outside. And there are fan bases who follow and study replays of pro gamers like Go did. StarCraft provides a good environment for deep learning, especially reinforcement learning, as it is capable of creating various scenarios using API and map editors. So why StarCraft is difficult to study? There are 4 big reasons why StarCraft is similar to the world we live in. First is the partially observed state, fog of war. In StarCraft, agents can only use the information that is available in its field of vision. Second is a long play game. Unlike other environments, there are 24 frames of information being produced per second with a long play time of 20 to 30 minutes. StarCraft has sparse reward, as the only reward one can take away from the game is the just winning of the game itself only. Third reason is a huge number of observations and actions being generated in a frame. Lastly, it's a challenging environment that requires agents to control multiple heterogeneous units simultaneously. The video clip on the left shows OpenAI's cardboard environment that all of you are so familiar with. Agent is the cardboard. In the middle, it receives 4 real numbers for velocities and angles of the cart and the pole. And it can move either left or right. It receives 1 reward point for each step that's completed, as a reward is based on how long one stays in a game. This looks very simple compared to next to the StarCraft next to it, right? Let me explain further using one of the simple scenarios we provide. This is a scenario where a cold virtual fight against 12 opposing juggling units. The agent virtual has to dodge terrain obstacles while destroying the oncoming 12 opponents called jugglings. It looks fun, isn't it? Let me explain how we design our agent to carry out an attack and come out winning. Reinforcement learning centers around 3 key points: observations, action, and reward. For observation, factors such as its virtuous health point, location, information on the movable distance in 12 different directions, and enemy's position could help virtual to decide on its action, right? For reward, virtual earns 3 points for attacking an enemy and lose 5 points when HP goes down and 10 points when enemy dies. Lastly, for actions, virtual can perform 13 different actions, 12 for reactions and 1 for attack. So as an agent will behave in the following way after learning the rules and strategy of the game. A smart agent then undergoes training 5,000 episodes, learns to avoid getting trapped in the corners of terrain features, and use kiting techniques to attack, withdraw rapidly, safely destroying the enemy forces in the end without losing any health point. You can create these smart and interesting agents by developing and running agent code. Doesn't it look fun? To develop a reinforcement learning agent, we can use StarCraft to define various problems that can categorized into 3 different levels: macro, intermediate, and micro, depending on the way they are engaged. At macro level, problems of a big scale, including overall management of resources from start to end of games, are addressed. At intermediate level, problems of smaller scale, such as controlling small-sized troops or formulating strategies, are addressed. At micro level, local problems such as controlling unit in battles, searching, or resource gathering, as shown in the previous slide, are addressed. Such categorization of scenarios allows us to engage a wide range of problems in a systemic manner. I will show you some of these scenarios in the next chapter. Now, shall we look at our SAIDA? This is a reminder. SAIDA stands for Samsung SDS, Artificial Intelligence Data Analysis. The SAIDA RL architecture structure is as follows. The one on the left is an agent, and the one on the right is an environment. On the far right is a StarCraft game and map information for scenarios. Of course, you can use SAIDA RL in environment other than StarCraft. In StarCraft environment, agent commands are executed through StarCraft games and Brood War API written in C++. Information is provided on the environment, and protobuf are used to exchange messages. And the shared memory is used to communicate with the agent. Agent can be developed with baselines and modules that are based on Python and Keras. Now I will explain further on SAIDA RL on 3 aspects: installation, environment, and agent. First, the installation. Our SAIDA RL is designed to run on a single window operating system, and the whole process from installation to execution can be completed in 5 single steps. And I would like to spend the next couple of minutes explaining the 5 major characteristics of StarCraft environment. At first, each scenario provides UI that shows agents' behavioral information, such as their moving directions, Q values, observation of agent, as well as enemy's position. You can use this visualized information to ensure that your agent is running well. Next is a standard metrics. Even a simple scenario requires some sort of standard metrics for evaluation of how well these multiple agents are doing in the actual game, which is why we defined our own standard metrics for each scenario. Third is multiple challenging scenarios with varying degrees of difficulties. The difficulty level, which is based on factors including number of enemies involved, presence of fog of war or terrain, makes the game more fun and challenging. The fourth is flexibility of environment. You can redefine environment in a way you want using parameters. For example, instead of processing 24 frames of information per second, you can control the frequency of how often agent takes the information and takes action accordingly. You can also decide on other matters, including whether or not GUI should be activated or an action should be continuous or discrete. Lastly, a multi-instance can help you to collect your sample quickly, enabling you apply parallel running algorithms such as A2C and A3C. We plan to add distributed running feature in the near future. Next is agent. As you can see, there are various baselines available, and we are constantly updating them. It supports many of the basic algorithms used, and we are upgrading by extending Keras-RL, a popular Keras-based reinforcement learning framework. We provide baseline algorithms and modules. You can use them as if you build just Lego blocks without having to implement it from the scratch, but focus on the parts that needs to be implemented. To implement agent, you need to reshape row observation and redesign reward. Then those code will be called frequently. For example, the pseudocode on the right is the queue running, and the part highlighted in yellow are what I mentioned earlier. Once we fill with the code using the processor or callback functions, we don't do that twice. Callback and processor that I explained in the previous slide are called like this to make the agent work. In the agent, you can redefine the row observation received from the environment in the form of state so that the agent can run well. From now on, let me show you some interesting demos. First demo is an agent, virtual battling against a single zealot. In this scenario, observation, this agent takes its enemy position, velocity, cooldown, health point, and reward is 10 points for killing an enemy, minus 10 points for death, minus 1 point for agent to be damaged, and 2 points for agent to attack the enemy. Action space consists of 13 discrete actions like this. And in this demonstration, agent virtual is dealing with 2 zealots, not 1. This makes the battle more challenging. This demo is a scenario where an agent Scourge arrives at a destination avoiding an enemy unit called Hydra. But the enemies are in a fixed position. They don't move. Let's see. Okay. And at this time, the enemy is moving. So for agent to understand enemies' moves, we added the velocity of obstacles into observation. You see. Okay. And in this scenario, the map is not small. It's the same size as the actual game map. And the observers then needs to be avoided keeping moving randomly. So for making agent moving up until the top of the map, which is the destination, we give another reward once agent break his record. There is a range of difficulty levels in the survival scenarios like this. Okay. And now it's about code. I'd like to explain that code is very simple. The agent-wide code is divided into 5 steps. First, we define the code environment. First, we define the environment and set the parameters. Then we create a processor that redefines row observation and reward. And then we define an agent. Agents define parameters which are policies, memories, and baseline algorithms to use. Finally, we define a callback, a module that draws a graph of your training status, and finally runs the agent. Isn't it simple? And this code shows that we express raw observation from the environment as a state that the agent will take. This code converts a list of X and Y into spatial information on the grid. And when implemented in the above processor function, the agent works by itself. This is the end of code, which defines the reward. Normally, rewards are not provided except for the simple environment. This reward design is of utmost importance in solving the problem. Here you can see how the previous observation is compared to the current observation to assign reward. Lastly, I would like to explain the activities and research we have done through SAIDA. As a mentor, Samsung SDS led a project with 8 students from Seoul National University and Hong Kong University of Science and Technology students for 3 months from May to August 2019. We carried out 2 projects of inverse reinforcement learning and multi-heterogeneous unit control reinforcement learning in parallel. Despite the lack of resources and time, students were highly engaging and enthusiastic throughout the project. So this is their result. So this demo shows a multi-heterogeneous agent learning. The agent learned using multi-agent bidirectionally coordinate net using BigNet, but we couldn't experiment enough due to lack of resources and tight schedule. But nevertheless, we were able to get a good result, relatively. You see that Dropship and Goliath cooperate each other to kill all jugglings under Guardian's powerful attacks. Though they didn't catch up to Guardians in a heterogeneous unit battle, but first of all, it's very impressive to see that different type of units help each other and learn each other to kill enemies. Okay, this demo is for inverse reinforcement learning. I think that this research is like a first step toward using programmers replay data as training data set. This research was to teach the agent to play like a human. So we used 2 algorithms, which were generative adversarial imitation learning and behavioral cloning. And the agent could learn 2 different styles, different type of playing styles. The first one on the left is a playing safely style. So the agent doesn't lose his health point. And the other one on the right is reckless attacking style to beat the enemy as fast as possible. Even if the agent loses his health point, he wants to finish killing the enemy. It took some time to see the result from the agent on the left, but it still followed the playing style of the human who play with a safe style. Okay, and our activity then began to solve 3 difficult questions now with 14 students who are well known for their expertise in deep learning in Korea, running the AI college program at Modularized. The final problem is to optimize the resource management of full-length game. So our next goal is to make a brain that makes decisions throughout the full game, and that's very hot topic. As you can see in the slide, many companies are doing this research through industry and university collaboration. And next, our research topic is to build a fast learning environment in a distributed environment. Since learning is too slow for current environment, I'm interested in building an environment where agents can learn with more resources. And in its conclusion, we are testing and verifying these reinforcement learning agents on our platform and hope to use this knowledge and experience for use in the real world. So this is last slide of my presentation. This is a photo of my team members and GitHub address of SAIDA RL below. I want to say thanks all my team members, and with that, I'd like to wrap up my presentation. Thank you for your attention. Are there any questions or feedback? Okay, thank you.
How did you figure out where all of the units are on screen? Did you use the data directly from the game, or did you screen scrape it and somehow analyze that?
Can I beg your pardon?
The units inside of the game, you somehow figure out where they are on the screen. The AI somehow figures that out.
Actually, we have a Proof World API. So through the API, we can extract the data as raw data. So we transfer as a state which agents can understand.
Okay. Have you ever thought about doing this more organically by screen scraping and having something else figure out where units are and somehow classifying what the units are?
Yes, of course.
What kind of API would you use for that, or what kind of AI would you use to do that?
Oh, I can't understand what your question. So maybe if you come up to me, maybe I will let you know.
Sure.
Thank you.
Thanks.
Any other question? Okay, thank you.